setting up the presentation, but I can already tell you what this is about. Unlike the previous presentations today, I'm not going to present an application. I'm actually doing a presentation about a library that can underpin future applications, and it's already underpinning my own work. But so far, I'm the only user. What I'm looking for is more users. So my name is look, that's perfect. My name is Alex Hakensanker. I'm a lecturer at the University of Surrey. I do research in land use and transport systems, and part of my research means having to work with rasters and doing creative things with them. And in order to do my creative things, I needed this library. It's as of the day before yesterday, it's an OSGeo community library. It means it's being recognized by OSGeo. It will be on their website, which is a nice advertisement for me, but it also means that at least they thought it was good enough to have on their website. So when I say we use the library for Map Algebra, it's a C++ library for Map Algebra, it is useful to first explain what Map Algebra is, or what I mean by it. And it's a conceptual model that is very widely used in geographic information science of classifying different operations that we have on spatial data in general and on raster data in particular. And there are 3 or 4 main types of operations. So we've got local operations, where we have 2 layers, and we combine them to get a 3rd layer. And all we do to get the 3rd layer is look at the same location and do some operation on them. So you might add 2 layers together by location or cell by cell, adding values. You've got focal operations, where the new value that you're calculating is not just a function of other values and other layers at the same location, but it's a function of the other layers and the cells or the pixels that you find in the neighborhood and in the proximity of the cell that you're calculating for. Yeah, so I'm calculating the sum of this neighborhood of 5 cells here. Value 1, 2, 3, 5, and 2. I add them all up, and then my outcome is this value 13. So that's a focal operation, yeah? Because there is this window and there is a focus. Yeah, it's also called a canal operation. And then there are zonal operations, which are basic again. When you have a zone map, you might calculate statistics for different zones. It's the focal operations that are computationally most interesting. All the other things just require you to go cell by cell over your data. So this may sound pretty basic, and it is actually pretty basic. And when I started working with this, I was assuming that there are plenty of libraries that allow you to do just what you want to do. And there are many libraries, and they all support Map Algebra in some way, and not just libraries, also tools and scripting languages and so on. There are libraries for dealing with raster data, there are image processing libraries, there are linear algebra libraries, because what is a raster other than just a matrix? There are scripting languages, there's PC raster, there's R raster, and so on. And of course, now there is your QGIS and your SECA-GIS and so on, CRAS. All of these do something, but none of them do everything. So what do I have in mind when I say, no, I want them to do everything? Well, I'm thinking about users like me, people working in geocomputational areas that do not like to be constrained by the specific tools and methods that are available. That if they have something in their mind related to Map Algebra, that they can actually implement it. And therefore, my most important requirement for my library is that it's customizable. And that is the main thing that is lacking in practically all existing tools. I want to be able to have a local operation that is just the function that I want it to be. Yeah? Not just the sum or the sine or the cosine. I want to write my own function and then apply it on a bunch of layers. If I do a focal window, I don't just want to calculate the mean or the variability. I want this focal window to calculate exactly the statistic that I want it to calculate. And again, that's not easily possible at the moment. Of course it's possible, otherwise I couldn't write the library, but it takes a lot of work. It needs to be scalable. It shouldn't just work with small data sets, because often our raster data sets are very large. Yeah, we might have a raster data set of Europe on a 200 meter grid, and it still needs to work. So that means that you need to have some kind of buffering going on, and you cannot just have all of the cell values in memory. It needs to be efficient, of course. It needs to be flexible. There are many different types of raster data, different formats, and so on, and I want to be able to work with all of them. It needs to be usable, and for me, being usable means that if I use it in a programming language like C++, then I want to use C++ language to work with it, and not some kind of invented macros and so on. I want to use the language features of the language to work with my data. It needs to be natural. And it needs to be compatible. That's another part. I don't want to have a tool that I can use standalone. I want to use my map algebra operations in conjunction with other analysis, because it might be part of a model, or it might be part of an optimization routine, or anything else. Yeah? So those are my requirements. The first thing is to come up with the right concepts to be using in the library. And I am basing my concepts on a concept that is currently very popular in C++, and it's the range concept. There's already a boost range library, and there is an official range proposal, and it's going to be part of the C++ 2020 version. You can find it online at that website. And a range is a very simple thing. It's a bit like a container where you have a bunch of values, and you can go from the first one to the last one. The only difference between a container and a range is that the range says, actually, you don't need to have all those values in memory. The only thing that you need is the mechanism to go from the first value to the last value. You might go in incremental steps, you might randomly generate numbers, or you might be a container and have all those values stored on disk or in memory. So that's the difference between a range and a container. Then there is the concept of the range view, and that's a special range that you can copy in constant cost. So that means that it's a range that you copy. You don't need to copy all of the different data values. Either you have a reference to the data values, or there are no data values to begin with. Yeah? My variation of the range is the raster. It's a range with some additional information. You can go from the first value all the way up to the last value, but it goes in rows, and every row has columns. So a raster is just a range of which you know how many rows there are and how many columns there are. And then I have one additional requirement. If I have such a raster, I should be able to get a sub-raster of it as well. So if I have a raster of 100 by 100 cells, I need to be able to access just 20 by 15 cells within that big raster. That's the only additional requirement that I have for my concept. And then we've got a raster view, can be copied in constant time. So in terms of C++ requirements, then this is what we need. So in order to be a range, we need our objects to have two member functions. Begin, to find out where's the beginning of my range, and end, to find out where's the end of my range. And all of the values go in between. And you've got an iterator that can go over all of the values. If you have a sized range, you also need to have a member function size. If it's a view, you need to be able to copy it at constant time. And then Here's the new stuff or my stuff. If you want it to be a raster, you need to be able to ask it how many rows do you have, how many columns do you have, and get me a sub-raster of you. Yeah? So those are all the requirements. If I write a class that needs to act like a raster, so that needs to conform to the raster concept, these are all my main requirements. Yeah? If I implement that, then I can do whatever I do in the library with rasters, I can do with that class. Oh boy. Doesn't all look grand, but I think the main thing is there. So this is how it works. You can just open a raster file, and after opening it, and open a raster file is not something that I do, it's something that another library does for me, the GDAL library. Yeah? And once it's opened, it adds this raster interface to it, and then I can use it like a raster. So I can have a very simple range-based for loop, and I can go over all of the elements in my raster and add them together. Simple as that. Likewise, I can open a file, and then I can say, go over only these 10 rows and 20 columns. And then the cost of this little program that opens a big data set and then iterates only over a small part of the data set is proportional only to that small part of the data set. Yeah? So you don't have the cost of the big data set. Okay, so that's a raster. Then let's look at local operations. So local operations, you've got a bunch of rasters, layers on top of each other, and cell by cell, you're going to do operations on them. And what the library does, rather than calculating immediately when I add two layers together, immediately calculating the sum of all of the cells, all of the pixels, it produces an expression template that postpones calculating the sum and only starts calculating at the moment that you're iterating over the values. Yeah, so the expression template that is the result of an operation on a raster is very cheap to produce because it's just the instructions to calculate something. It's not actually calculating something. Then, only at the point that you're iterating over the values, you're calculating them. And that has benefits because that means you can add two rasters together, do another function on some other rasters, and another on some other rasters, and all of that is very cheap, and then you can combine them, yeah, with another function, and then iterate over them, and you can have this whole compound expression of raster algebra, which you're only going to iterate over your values once, and you don't need to produce any intermediary values, yeah? So you don't need to create raster dataset just to store intermediate values. There are no intermediate values. Everything is resolved at the moment that you're iterating over the values. So that makes it more efficient. And also more robust because you don't need to write to disk or anything like that. There is in the library a very generic transform function where you can just give any function and apply it on any number of rasters. So here's an example. Open two datasets, A and B. Apply the transform function using the function plus on A and B. That's cheap, that doesn't cost anything, that line. And then iterate over this sum. Yeah? And only at the moment that you're iterating over it, now you're incurring computational cost. And because you use the sub-raster here, you only iterate over part of the raster, you only pay the price of adding those pixels that you're actually looking at, and not the whole raster. What happened there? Sorry, guys. You know how to flip it?
Oh, I don't know how you do it.
I don't know. I touched something.
Well, just leave it because we will lose too much time if we
Yeah, I'm leaving it.
change.
Yeah, I know, but the mouse is here and the button is there, so I don't know. Can you manage that? We continue like this.
Yeah, just talk and I will
Yeah.
pick it.
So what this example shows is that you can combine two transforms. Yeah. So I had the first transform that does the minus. Ooh. Yeah.
Last slide. Yeah, I'll let you do it.
First transform that does the minus, the second transform that does the squaring, and you don't need intermediate results to combine those two operations. This transform operation can be quite cumbersome, and you can use it as a building block for other operations. So you can overload your operator minus and your operator times, multiply, and you're actually adding rasters and multiplying rasters cell by cell. This I will skip. I just want to tell you that in working with raster data, we often have missing values, and working with them can be cumbersome. But in C++, we have the optional data type, and this library uses the optional data type for missing values. So it becomes a very logical way of dealing with missing data. And every function that produces missing data knows how to do it, and every function that can account for missing data knows how to recognize it. There are a bunch of functions that do some kind of spatial transform that do not copy data either. So again, they're being efficient by not copying data, but just by referring to data. And one function is path, which adds trailing rows, leading and trailing rows and columns to a data set. So you just put a frame around it, make it a bit bigger. We've got subraster, which I already mentioned. We've got offset, which for every cell gives you the value in another layer at a spatial offset. So a few rows to the left and columns to the right, something like that. And you can iterate over pairs of adjacent cells. And all of that is being used when you're going to do focal analysis. And one very popular form of focal analysis is moving windows, where you have this window that moves over the map, and you calculate the summary statistic for the window. Yeah? And if you want to do it efficiently, you do that as a big fat combination of all of these expression templates, so you don't need to create any intermediary values. And that is possible because there are moving window schemes where you say, if I've got my summary for a pixel, then I can get the summary for the next pixel by adding the cells to the right, subtracting the cells to the left, and then I've got my next window. And I can move it again and again and again. So you can increment, if you've got some kind of online statistic, you can incrementally move a window over the map. And as these pluses, which are the cells that are being added to the statistic, and the minus, those are the cells that are removed from the statistic, as you move over the map, these move in exactly the same pattern. So all you need is a range for each of those offsets that does all of the adding. So you can make these moving windows using the simple offset function and using the range view concept, and it will be relatively cheap. And if you separate the logic of the window moving over the raster and the statistic being calculated, then you reach this ideal of being customizable. Yeah? So if I express all my statistics in forms of adding elements and subtracting elements, or adding groups of elements and subtracting groups of elements, then I can implement any statistic that I'm interested in this moving window framework. And again, this is how it works. You open a map, you specify the window, you specify the indicator that you want to use, and then you just have a function that says, this is my moving window. And all of that is cheap, and it only gets expensive at the point where you're going to iterate over that window. And again, you can do it for a subset of the raster. This I will skip. This I will skip. So one problem, I can just say what it is about. One problem with all these concepts and templates in C++ is that you get very complex classes that are a compound of all kinds of things. And you can use type erasure to make your complex classes simple again, so that you already at runtime know what classes you have. That you can look up, I would say. So what's another big advantage that I'm not taking advantage of yet, but I plan to do it in the future, this sub-raster idea, that you can set up your expression for the whole raster and then evaluate it only for a part of it. That is of course ideal for parallel processing, because I can have my expression for my big raster and then say, do this block, then this block, then this block, then this block, and so on, and do all of that parallel so that it goes more quickly. And actually, it's already there. The functionality is already there. The only thing that needs to be done, the rest of the library needs to be thread safe, and especially the part of accessing the raster data is at the moment not thread safe. So it's not parallelized yet, but the architecture is there to actually do it. So what kind of applications do we have? We use it, or I use it, for cellular automata land use modeling. I use it for skill-dependent landscape analysis. I use it for fuzzy set map comparison, and all of these things can be done very efficiently thanks to the clever design of the library, I would say. So the conclusions. I wanted it to be customizable. Yes, it is, because you can use any function for local operations, and you can use any function for moving windows. I want it to be scalable. Yes, it is, because it's built on GDAL, and GDAL is scalable. I wanted it to be efficient without temporary files. It is, because of the expression template. I want it to be flexible and usable, and I think all of that is achieved. So it's open source, as it should be. You can find it on this website. If you've got any questions, and as I said, I'm looking for users, so if you need any help getting it to work for your project, I'm happy to help as well. So if there are any questions, I'm happy to answer them. No questions. Yeah.
Did you try to push it to keep the environment?
No.
To make it passive parallel?
No, I didn't do that. No, I did. There is potential for parallelizing, but I haven't actually done it. Yeah.